Let's look at a slightly larger example in which we want to have a dialogue of the form where we ask the user something, and then depending on what the user answers, we either want to do the same thing again, namely ask the user something, or we want to stop. Okay, so let's just start. I mean, we're going to call this conversation, even though it's going to be a very repetitive conversation, and we're not really interested in the final result. And we're just going to start by asking for something. So perhaps we say, please provide some input. Okay. So that is a put string line that we've seen before. So that's an IO unit. And I can use bind here in order to sequence with the next thing, but I can also just use the greater because it's a unit result anyway, and I'm not interested in it. So the next thing I want to do is the get line. Okay. And here I'm going to use a bind, and I'm using the style where I'm going to put one IO component action per line, and I'm using the bind with the lambda abstraction on the same line. So we call the result of the get line x. So that is our result now. And now we're going to check whether some input has actually been provided. So whether the user has just pressed return immediately. So that would mean that the list that we get back, the string, is empty. And we can check that with the null function. So we can check if x is null. And depending on this, we can do one thing or another thing. Okay, so now in both these situations, we still have to provide an IO unit action. Okay. And now, if the string is actually empty, then we are going to consider this as an indication that the user wants to stop with this strange conversation. So we're going to say one more thing, namely bye, and then leave it at that. So that is our final IO action in this case. But if we are in the other case, we're going to say something different. So perhaps we're going to actually say thanks for the input, and then I'm actually going to list the input again. So x in parentheses here. Right, and I need the parentheses around the argument because of these invocations of ++ here to concatenate all the strings. But now I want to continue, and so I'm going to continue by calling conversation again. And here we see recursion in action in order to express looping. Right, so if I try this one out, then I'm being asked to provide some input. All right, so I can say something like hello. And then, as you can see, I'm getting this message, thanks for the input, hello, please provide some input again, because we have restarted conversation. Now, what's next? This is interesting. And then we get, again, a loop. And I can go on until I'm getting tired of it, and I just hit return, and then I get the response by, and I enter this branch. Now one can do other things that we have been seeing before as well, of course. We have already been defining our own functions in terms of I/O. But certainly this combination of putString line and getLine, that makes sense to abstract from. Right? So you can say something like ask that gets a string as an argument and an IO unit, actually an IO string as an output, and is exactly this combination of putString line and getLine. So we ask a particular question, or we give a particular prompt message. So we put out this prompt, and then we do getLine. And here I don't even need to use another bind or pick up the result, just the result of getLine using basic sequencing is actually the result I'm interested here. And if I've abstracted from this particular combination, I can simplify the definition up here in such a way that I don't need this first sequencing anymore, but I can simply say ask provide some input, and then at this point I go on. Now you can see that if we start writing programs in this style, right, like we've done here with lift A2 with the re-implementation where we put these lines on lines of their own, or here in this style, or here, they almost start looking a little bit like imperative programs, in the sense that in imperative programs we often have an assignment, and we can write things like x equals, and then some result type, and then semicolon, and then the next thing. So there are often these sequences of statements that are separated with semicolons. We can have assignments to give names to the results of these statements, and continue using them. And this looks a bit similar in style. So for every bind invocation, we are having some sort of sequencing. We can give names to the results, or we can not do that if we choose to do the basic sequencing. But nevertheless, we can chain multiple instructions, and it has a look and feel a little bit of doing imperative programming inside of Haskell. And that's to some extent what it is, because as far as we are in the process of constructing an I/O action, then we are doing some form of imperative programming. We are very much concerned with sequencing, which is one of the basic building blocks of imperative programming. And to take this analogy a little bit further, Haskell actually has a special language construct that is called do notation that makes this even more pronounced. And do notation is just a shallow syntactic layer, so-called syntactic sugar, that actually is internally translated into a sequence of binds and basic sequencing operators. So the things that we have been seeing so far, that we have been writing using binds in our code so far, can all also alternatively be written using do notation. Let's use this conversation example as a starting point, and then go on to transform some of the others as well. It's just a different syntax. We're not changing anything in the way that the function actually behaves. So you start a do block by saying do, and it's relatively common to use this hanging notation for do blocks, where the do actually comes directly after the equals, and then you still start indenting just a little bit. Alternatively, I could write do here on the left, but then I would indent the next line even more. Right? But this is a rather common thing. And then you see that things are currently incorrect because they then behave slightly differently. Then you put one IO action on one line, and if the IO action has a result, so if there is a bind following that picks up the result, you can put the result of the IO action to the left with a left arrow. All right. And now the X, just like here, where ask please provide some input, returns an IO string, and X is of type string because it gives us access to the result of the previous action. That's the same thing here. If we say ask provide some input, this returns an IO string, and X is a string, right? And then on the next line, you put the next IO action, and that's actually currently the case because the then and the else are indented with respect to the if, so this is all considered to be one statement within the do block, and they all have the right type. And if you want to do the same thing here, because we have another sequence here, put string line, thanks for the input and conversation, then we have to start a new do block, because the outer do block here is essentially on this column, and it spans these outer statements. But here we are within the if then else, and if we want to sequence again within the if then else without having to use a sequencing operator, we would have to start a new do block. So here I would have to actually put this on different lines. But this works, right? And then I have my conversation prime program that works in the same way as the conversation program. And I can do this for all sorts of other things as well, right? I mean, I could rewrite the ask function to use do notation. And if I've already been careful in putting things onto different lines, that is actually a rather straightforward transformation always. Right, let's go to this lift A2 prime. That was already a rewrite of lift A2. So we can rewrite this again using do notation as well. Right. Remember, lift A2 was this function that takes an operator and then two IO actions, puts the two IO actions in sequence, and uses the operator to combine the results. So we run the first action, give its result the name A, run the second action, give its result the name B, and then use the function f to return the two results. And because the function f produces a C, a plain C, we then have to lift the result again into the world of IO actions, turn that into an IO action again, so therefore return. So if we do it with do notation, the only thing that changes again is that we say A left arrow here, and we say B left arrow here, and we can say return just like that. Let's look further up. fmap could easily be written using this as well. Here, shout back twice is another interesting example because it has a let. That is one other thing that is a little bit special and do notation. So here I start with getLine, right? X is the result of getLine. And then here I'm saying let y equals map to upper X, because y is a list of strings. So here I'm performing an operation on a string, which is X, that takes it to a string that does not involve any IO. So this is not something that I directly have to embed into my sequence. I just want to give it a name because it's a pure sub-result, and I want to reuse it multiple times. And I can still do that in a do block. But if I'm in a do block, I don't actually have to use an in. I don't have to write in now, because I have this implicit scoping of all the statements in the do block in sequence. And if I make a let binding within a do block, then the y is now automatically available in the rest of the do block. I do need to put something after the let, so this is syntactically incorrect if the let is the final statement in a do block. That's why it was underlined. But the moment I put something afterwards, you can see that the red underlining goes away. Instead, I'm now having a warning that the y is introduced but unused. But now I can just use it, right? And I can just use put string line y and put string line y again. And here I'm still in the outer do block. I don't need to introduce a new do block because there is no in, and the let is just scoping. I mean, the let statement is just for this one line. And then I can see that shout back twice with the prime. Still works as before. Not in scope. Did I probably not save and then not reload. Oh, I know. Oh, did I did just mistype. That was the problem. So now, if I type ABC, I get the capitalized version of ABC printed back twice. So that is do notation. And with do notation, we can easily do all sorts of different things. Whether you use it or not is ultimately your choice, right? I mean, I think it is slightly more idiomatic in Haskell code that does I/O to use do notation than not to use it. So I would advise to use it. But there are still small situations, where writing something like using a single invocation of basic sequencing, or using a single invocation of bind is just very compact, and you don't need to be forced to, don't need to feel forced to use do notation. A few things that I still want to say about do notation before ending this video are that do notation is really all about sequencing, right? So the point what do notation gives you is that you don't have to use these sequencing operators. If you have a sequence where you don't pick up a result, right, then it gets translated into basic sequencing, and if you do pick up a result, it gets translated into bind. But if you have no sequence, then you don't need do. So if I just write a wrapper about, I don't know, on a call to put string line, for example. So perhaps I write another little abstraction function, whereas I get a message or a question, and I call put string line on that question, but because it's a question, I'm going to add a question mark in the end. So this is a single call to put string line, and it has result IO unit. So we don't need to put do there. This is redundant. Do in front of a single expression and no sequence of statements is just the same as not putting the do there. And some programmers get into this reflex that they say, well, okay, there is something of IO type here, I immediately put do there. I think that is confusing. Do suggests there's a sequence of things you want to do. If you have do followed by just a single statement, then it's redundant and you should probably omit it. Okay, so actually Haskell is very liberal when it comes to the introduction of do. You don't need to use it with IO statements at all. You can prefix any expression with do because it is redundant, any single expression. So, for example, I can say do of 1, 2, 3 in order to mean the same thing as the list 1, 2, 3. And I can even, because I can do this once, I can even do this twice. I can say do of 1, 2, 3. Or I don't even need the parentheses, I think. So you can write really strange programs. So for example, if I want to add 1 and 2 together, I can write do 1 plus do 2, and build a program out of lots of do's. But don't do this, right? Please. I mean, only use do in the context of I/O operations, at least for now. Right? We'll see that do is actually, the do construct is more general than that. But at least for now, only if you want to build I/O actions, and only for sequences of I/O action in order to actually simplify something that you would otherwise have to write using basic sequencing or bind, things like that. Right? The last statement of a do block cannot have an arrow, right? The last statement of a do block is special in that way because the last statement of a do block determines the result of the overall do block. And so the last statement that occurs in a do block, so in this outer do block here we have the entire if then else, that is the outer do block, must have type IO unit, and it does in this case. And also in this inner do block, the last statement here, conversation, cannot have a result and must be of the type of the whole do block. For ask here, we have the same situation. Get line is the last one. It cannot have a result. I mean, not an explicit result, not something we pick up with a left arrow. This would be nonsensical because there's nothing coming afterwards where we could still use this. Instead, the result of get line becomes the result of the overall do block. Don't fall into the trap, even though it is often the case that return must be the last statement in a do block, right? We have seen many examples here already now where there is no return being used at all. That is not always the case, but it does still often happen. So you still have a situation, you often have a situation where you want to do multiple operations, and in the end you want to combine the results in some way and do not do anything further. And then return is the right choice. Also, don't fall into the trap of being misled by the name return or by the fact that return in many other languages has a control flow aspect to it. In other languages, return is often being used not just to return a result, but to actually signal that you want to stop with the current function and abort the computation at this point and somehow jump out of the current context. Right? That is something that return does in some other languages, not in Haskell. In Haskell, really the only thing that return does is taking a value and embedding it into an I/O action. So actually, we could use return within, where do I have this? Within an I/O action as well. Here, for example, rather than writing let y equals map to upper X, another option is to write return of map upper X. So now the result of this is an I/O string, right? Because map to upper X was a string, so return map to upper X is an I/O string. So now this is an I/O action, and now I can pick up the result of that I/O action again in this sequence using bind, essentially, right? Because this syntax translates to an invocation of bind, and then use the y twice. And now I have a return in the middle of my action, And there is no, it doesn't mean that something is stopping here, right? It's not as if the input string line y and input string line y would now not be executed. All we're doing here is we're turning this otherwise so-called pure computation that would not involve I/O into an I/O action, and then we're picking up its result again at this point. Doesn't do anything particularly special. Here we even know exactly what y will be, right? Because there is no actual side effects going on, so there is no nothing left to chance as to what the result of this particular I/O action will be. It will be exactly mapped to upper X. So in situations like this, I would say the let is better, right, than the use of return. But I'm using this as an example here to just make it clear to you that there is nothing magic about the behavior of return. It does not do any control flow things. It does not do any jumping. And if we reload once more, and if we execute shout back twice once more with this return-based form, then we see that it still works as before. So let's go back to the let version before I end this video, because I want to leave the recommended version on screen. I think that's enough for the time being. So we've been writing slightly larger I/O programs. We started with this conversation which has a loop which uses recursion. So that's our first step to getting back to functional programming constructs. So next we're going to look at this recursion aspect a bit more. And then we've been introducing do notation. And as I said, I mean, we are going to probably write most of our code using do notation from now on. And then we've been translating a couple of things into do notation. We've been discussing some aspects of do notation, such as that you have to be putting nested do blocks inside of some other constructs, but also that you have this let construct available within do blocks, where you don't have to use an in if you want to temporarily define other pure values in terms of things that you've already computed. And then we've been talking about the role of return a bit. Okay, that's all for now.